So I will talk about walking technical and electroweak phase transition calculation. Well, this is the title of the talk. So I'm planning to give a rather long introduction to these walking technical models which have been discovered recently. And then I will talk about how we use low energy effective field theory for describing the dynamics in this kind of theories. In particular, I will discuss the effective theory of minimal walking technical. And then I will discuss the finite temperature calculation. So we are using the effective potential method to analyze the phase transition in these walking technical models. In particular, I will discuss calculating this parameter which characterizes the strength of first order phase transition in these models. I will mainly discuss minimal walking technical and then this other model which is the ultra minimal technical. And I will start with a brief introduction to technical in general, so that the idea is that you take away the X center of the standard model, which is kind of ugly. You have problems, and then you basically put these Higgs potential terms by hand. So you replace that by the technical theory. So the overall gauge structure is something like this. So in addition to the standard model gauge groups, you have a new gauge symmetry, which is the technical symmetry. And now the idea is that, in this new gauge theory, which is a strongly interacting theory, you will have a chiral symmetric breaking just like in QCD. And because you will link this to the weak interactions, the chiral symmetric breaking will induce the electroweak symmetric breaking in the standard model. So, because you don't have the elementary scalar Higgs, you would get rid of the hierarchy problem. And one thing which is clear from the start, so by adding the technical theory only, you never get anything which is complete. You have to, in addition, you have to add some additional interactions which come at much higher energies which complete the models. You did get gamma interactions and stuff. But the first problem is, of course, to construct the technical theory. And some motivations for technical in general is, you have never seen any elementary scalar particles. So this motivates to taking away the Higgs and replacing that by fermions. But instead of any elementary scalars that would condense and break the electroweak symmetry, you have seen technical symmetric breaking in nature, of course, in QCD, which is the main motivation, and then but also in superconductivity, where you have Cooper pairs, so the fermions form bosonic object which then condense, and it's probably quite closely analogous to QCD. And it should be bear in mind that QCD does break the electroweak symmetry. So, but it does it at the wrong scale. So,
sorry, how does that work? Does it not couple the same way to all flavors?
I mean, there's I don't see any particular difference. Why should it couple in a different way? I mean, it's not just in the same way as technical.
Mm-hmm.
I mean,
No, I mean,
yeah. So it does.
Condensation.
yeah.
That breaks. I mean, if the electroweak symmetry were not broken by Higgs, QCD would break it then
Yes,
later.
yes.
This is of course the point.
Yes.
Because
So
it's
you
broken
could
by
get-
the Higgs,
yes.
this doesn't happen. But
Yeah.
if there were no
Why is
Higgs,
that?
the scalar condensate breaks the left-right. I mean, you cannot have mass terms. Mass term. Sorry, you. When you have a scalar condensate, I mean, it breaks the
Yeah.
quark. V2 charged fermion condensate that breaks the electroweak gauge symmetry. Like adding a mass term breaks it.
So yeah. So this breaking will keep a
You
contribution.
cannot have
to the-
left-handed fermions with the mass term.
So this QCD breaking will give contributions to the W and Z masses of order 1V, MEV or something. Yeah. But, well, the most natural idea would be then to use the, well, exactly similar theory as QCD, otherwise except at much higher scales, well, at electroweak scale of few hundred GeV, which would then give you the correct, well, electroweak symmetry breaking at correct scale. But it does not work. There are problems with, well, first of all, it's very,
Sorry.
yes,
So it's spontaneous as well. Then the QCD breaks into.
yes.
Because there's no difference between the quark species anymore, right? QCD doesn't see any difference.
Yes.
So it just chooses some direction.
Does not have anything to do with the flavor.
Right.
Yeah, well, first of all, well, it can be shown. I won't go into any details, but if you have running dynamics, I mean, in QCD, for example, in QCD, the coupling constants, well, depends logarithmically on the scale. So then you very easily get, well, when you try to introduce some extended technical interactions, you get, and try to get reasonable fermion masses, like reasonable Yukawa couplings, you have serious trouble with flavor changing neutral parts. But it can be shown that if instead of running, the behavior of the coupling constant of the technical theory is such that it walks for a large scale of energies, such that you probably can't see the label, but this is the coupling constant as a function of the logarithm of the energy scale. So for a large range of energies, the coupling constant is almost constant. So this is the walking behavior, and so that means that effectively your beta function will, well, instead of the typical QCD beta function which would go straight down, you will have something like this, where the beta function is very close to zero at some critical value of the coupling. So this kind of beta function corresponds to this behavior of the coupling as a function of energy. And it can be shown that in this case you can reduce the flavor changing neutron currents while keeping reasonable fermion masses. But this is, well, the other problem is then the electroweak precision test. So in particular the electroweak S parameter, because, well, in particular, if you want to tune your QCD-like theory in such a way that it has walking dynamics, so well, you cannot really calculate what their S parameter is in this theory, but you have some estimates and they show that it should be huge, so much larger than the bounds which come from the lab measurements, like an order of magnitude larger. So this is the death of technical. But well, a few years ago, Salmino and Tuominen came up with this new class of theories where well, the idea is that, well, I will show some diagrams in a minute, but if the technique works transform in some higher dimensional representation of the technical gauge group, for example, the absolute representation, then you can have the walking dynamics at just such low number of fermions that the contribution to the, well, S parameter is suppressed. So if you calculate the most naive perturbative estimate to the S parameter, well, it's proportional to the fermion number, so that's why you want to reduce it. And well, then in addition, there are there are some reasons to believe that S parameter is further reduced by this walking kind of dynamics. And then one thing is that you cannot really compare the S parameter which comes from the technical theory directly with the experiments, or because there might be additional contributions, because the technical theory itself is never a complete extension of the standard model. So you know from the start that you have to add something else, and that those might also affect the S parameter. So I mean, you cannot really kill the theory by measuring this thing.
Sorry, what's the S parameter?
Well, so the definition of the S parameter is a bit technical, but it has to do with the, well, you can measure it by, it's linked to the properties, well, the measurement is linked to the properties of, so the strong interactions affect the propagators of the Z and W pulses, so you have some kind of fluke corrections. You can, these modifications can be linked to some parameters, S, T, and U usually, the skin W parameters. Well, but this S parameter is like the most important for the technical theory, so usually large contributions. It should be, well, the standard model value is defined to be 0. And in these technical theories, you usually get larger contributions. Okay, so then I should discuss how do you actually find these theories which or specific models which could be walking and have small contributions to the electroweak precision parameters. So you want to have a low number of technicals, and then you have to find a theory which is walking, or has the theta function which, well, almost has an infrared fixed point at some critical coupling. And well, first of all, these have been analyzed by using some Swinger-Dyson methods, and then also some by taking an analog to this supersymmetric Young-Mills theory and the beta function there. And more recently, there has been really, well, okay, there are many groups working on this kind of theories on the lattice. Well, I didn't even try to include all the work which is being done there, and I'm not really an expert on these things. I won't discuss, but maybe Kari will.
So this S parameter is the only problem of the technical.
Well, so I mean the main problems are the flavor changing intercurrents, and then they are too weak. But well, so okay, so I will now show you the phase diagram of these the SU, well, actually the SUN theory. So I should explain what is shown in these plots. So this is this is a function of the number of colors and the number of flavors. And well, if, for example, if you take a fixed number of colors and then increase the number of flavors, at some point you will get a beta function which is positive. So you expect that you will have, well, you know, actually you can calculate the first coefficient of the perturbative beta function. And well, this is the line where you lose the asymptotic freedom of the theory. So above this line you have a free electric theory where your beta function is something like this. And then on the other hand, well, for a low number of fermions you will have a QCD-like behaviors from here. The beta function looks like this. And then, but then in the middle, well, somewhere here you have the conformal window where your beta function behaves like this. So you have a true infrared fixed point, and the theory becomes conformal in the infrared. And now the main problem is to, well, and then there is some line where this behavior changes, and from conformal to, well, this QCD, like, well, near this line, then you will expect to have some working kind of behavior. But this is the most, well, this is really infrared dynamics, and you cannot solve exactly in the strong, which you cannot solve exactly in the strongly interacting theories, but you have different estimates. So what is then shown in the plots, well, are these lines for in the SUN technical theories for technical works in different kinds of representations of the gauge group. So this is the black lines are for the fundamental representation. So this is the line where you lose the asymptotic freedom. And then there are different estimates for this, the other line which is the lower bound of this conformal window. Yes. So the dashed line comes from the Springer-Dyson analysis. And these solid lines are actually conjectured lower bounds for the conformal window. So you expect that the lower edge of the conformal window is somewhere here. And well, this is for the fundamental representation And this is for two-index antisymmetric representation. The red one is two-index symmetric representation, and then the green one is the adjoint representation. Well, the most interesting thing here is that you see that for the two-index symmetric and adjoint representations, these bands are very low. So that means that you can reach the conformal behavior for a very small number of technique works. So you expect that somewhere here you could have possibly working theories. And well, by just looking at this diagram, you can...
So walking is just at the lower edge?
Well, it's
Somehow?
it's just...
It's below
It's
the
actually-
conformal line.
Yeah, so it's just near the, there is some line where the conformal behavior is lost, so you want to be just below this line.
So that's just below, say, the white stuff.
Yeah. You don't know exactly where the line is, but it should be somewhere here.
But of course, I mean, it's a thing is that this is now coupled to standard model particles and so on. So this is much more complicated in that way. You have additional interactions, so that especially this window might get kind of blurred. That even if this theory would land in the conformal window, it might be that coupling to the rest would then break this, so that you don't get conformal behavior, and you will then get
So is
walking-like
anything equals 1?
behavior.
That probably would be like that.
Sorry?
Nf equals 1?
Sorry, I didn't...
Nf equals 1.
Oh, NF equals 1.
Is that probably too far away?
Yeah, I think it's too far.
Okay.
So, because this solid line should be lower bound.
Yeah.
I think it's too far away from that.
Okay.
And well, so then you can pick some candidate theories. For example, this point here, this is minimal walking technical. And there are some other theories. So the minimal walking technical is, well, two Dirac technique folks in the adjoint representation of SU2, and there is next to minimal walking technical is two Dirac technique folks in the two-index symmetric of SU3, and then there is some more complicated model which I will also discuss a bit if I have time, where you actually take technique folks in two different representations. Okay, and then I will, quite briefly try to discuss the low energy construction of the effective fields theory for these kinds of models. Well, this is in general. I will then, I will briefly I will in a few minutes I will give some examples for the minimal walking technical. So what you do is just analogous to the chiral perturbation theory in QCD. So you write down an effective field theory which has the correct chiral symmetry breaking structure. So you have the chiral symmetry group G, which is fixed by the underlying gauge theory. And then you identify the subgroup where the G is expected to break down to the chiral symmetry breaking. And then you, the way you couple the electroweak gauge symmetry to the technique forms then tells you how you should embed this electroweak gauge symmetry group into this chiral symmetry group G. And then if you, if the subgroup where you break into is if you are lucky, then you have the correct, you have such a subgroup that this chiral-symmetric braking induces the electroweak symmetric braking in the correct way. And well, what we have been doing, so you write down an effective field theory which describes the dynamics of the lightest composite scalars and vectors in this strongly interacting theory. Well, you can do it actually in different ways, and then you have like many different free parameters which are not, well, you have an effective theory, all the couplings of all the higher order couplings of the particles are basically free parameters. And well, there are some reasons to believe that these technical theories which we are studying actually have a rather light scalar particle in the spectrum which may be identified as a composite Higgs, which pretty much plays the role of the standard model Higgs, but it's just composite. And well, I won't discuss in detail, but we also use the Weinberg-Sum rules to restrict some of the couplings, well, which are some of the couplings actually of the vector resonances. So, well, to get rid of one or two otherwise free parameters in this theory. But well, let me go to the minimal walking technicolor. And just to remind you that the structure of the theory, well, so you take the standard model and replace the Higgs by two flavors which transform in the adjoint of the SU2, which is the technical gauge group. And well, what I didn't tell you before is that this, well, if you only add this, you have a problem because the theory is anomalous. It has this Witten anomaly because there are some odd number of fermions which are gates under the electroweak SU2. But this can be, well, there are probably many ways to get rid of the anomaly, but the easiest one is that you introduce as well as an extra family of technique quarks, you introduce an extra pair of leptons, which are supposed to be, both the neutrino and the electron are supposed to be so heavy that they are not seen in the present experiments.
So what is the role of the neutrino and the electron?
I mean, these are only introduced to get rid of this Witten anomaly of the theory. This is just the simplest way. But because these do not couple to the strongly interacting theories. Very strict. They don't essentially couple to the strongly interacting theory, but they could be also replaced by something else. But this is, anyways, the model which we are.
Is there a danger that this extra neutrino would get decoupled in cosmology somehow and affect?
Yeah,
Well, that's not the, I mean, that should decay, of course, I mean, very rapidly if left alone, I guess, so it cannot be dark matter, but
so they are
or is it?
Yeah, but no, this is well, there are some dark matter candidates
What does
in
it
this.
couple to this neutrino?
Sorry?
What does it couple to? I mean, does it have?
Oh.
SU2.
Yeah, so this is charge on the electroweak.
Yeah, so it could as we can
Yeah, it could.
Okay, so there are
Very heavy dark matter, yes.
So these both families, leptons have been studied. But I have not done that, so I'm not an expert.
But the problem is that the other one is charged, right? Yeah,
Yeah, actually
It
there's
also gives some.
It's not stable.
actually they could be both charged.
It's not stable.
I mean, there's a way to
But
assign the charges in such a way that actually they would be both charged, I think.
So you have to introduce a new charge to make this neutrino stable. If you want to make it dark matter, it's not automatically stable.
Yeah, well, I think in this theory there are some dark matter candidates, but okay, well, I think the possibility that okay, I'm not too familiar with the dark matter side of this thing, but I think the more promising thing is some composite of composite of these new objects. Some of them actually there are some baryonic meson, baryonic like 2 quark states, which are more promising, I would say.
So these new fermions, they're now charged on SU2 and under SU2.
They are charged only under the electroweak. I mean, they are just
Those guys, but
But the quarks, the
The
new
quarks.
quarks,
yeah, these are charged under S.
SU2 and
under
SU2.
SU2.
But not SU3, U1.
No.
No.
I mean, these are charged under the okay,
Right.
under the electroweak in exactly the same way as the standard model.
But not under SU3 because that would break.
Right.
Yeah, so this is
And the new neutrino is only on the usual SU2 and
yes,
U1.
yes. So it's just like the other leptons, but these are expected to be.
Yeah, the theoretical motivations for the new leptons is just to cancel anomalies.
Yes. But
So
yeah.
Okay, so you have a whole new family of basically 4 fermions. It's just that the 2 new quarks don't couple to SU3 but to SU2 instead.
Yeah, I mean, the QCD is complete. QCD part is completely like irrelevant for this.
And but so this bound from the Z width, etc., that's gone away because it's a very heavy neutrino and stuff.
You mean the S parameter?
Maybe that's the S parameter.
Yeah, I mean that has to do with the effect of the coupling of these new things to the electroweak sector.
No, I just remember this picture about the width of the Z, which shows that you have only 3 species of neutrino.
Oh yeah, but that's
very
for
heavy.
that's for very the light neutrino.
Light neutrino,
And this can be heavy.
Right.
Or you have to assume that it's heavy, otherwise you're in trouble.
But okay, so anomaly cancellation doesn't care about that.
That's ultraviolet. But could it give some signature? I mean, if it were arbitrarily heavy, you would see. I mean, it would be effectively violated with an anomaly somehow and restored only at very high energies. I mean, is there any signature for that kind of behavior?
Well, I don't know.
Do you have right-handed neutrinos, or do you not care?
Well, I think you can do quite many things. I mean, with
You
the,
don't care. That's all right.
yeah, but I won't discuss the dynamics of the leptons at all. I mean, I will just add the,
Actually, it cannot be dark matter because if it's charged on the SU2 left, it has a large interaction with the ZH bond. It would have been seen in direct detection experience, unless the mass is 100 TeV.
Yeah, it has to be very heavy anyhow. Yes.
so the minimal Wolfman technical, well, the naive estimation of the S parameter is 0.60, so it's reasonably small, so you can, it's of the order of the error bounds, the present error bounds of the S parameter. And then, well, this has been studied on the lattice, and well, it's certainly conformal it's certainly much different from QCD. So it seems to be conformal or working, and I think more recently it seems that it's actually conformal.
Yes, yes, I will talk about that later.
But as you said, then you can couple it to you need to couple it to standard model and maybe to something else, and then you can know what is the result. And well, okay, so the chiral symmetry group in this case is actually SU4. Well, what you would naively expect is that it's the same as in two-flavor QCD, SU2 left cross SU2 right. But in fact, because the absolute representation of the technical or gauge group is real, you can arrange the four Weil technique quarks. These are actually Weil spinors in such a array, which have the same transformation under the Lorentz, and so all the components have the same Lorentz and technical transformation, and that's you see that you can then you can your chiral symmetry is such that you can mix all these components instead of just mixing the left and the right with each other. So this is then your chiral symmetry transformation. And
So do you have, so now you're going to have condensate, which is going to be like a Higgs, etc.
yes.
Do you have something like recover coupling?
Well,
so
these are coming out from the extended technical interaction.
Right, so that's
So you don't know what these couplings are, but
So
you have to assume something. So what? Well, I will actually show you the Yukawa couplings, but we do it just like in the standard model. Basically, it's in such a way that you couple the composite Higgs to the fermion. So the composite Higgs gives the mass just like in the standard model. So that's the most economical thing.
So you have a sort of you have coupling. You have the usual fermions coupled to condensate. So it's like sort of 4 fermion.
Yeah. So
thing.
yes. So the extended technical interactions at some high scale give you at lower scale these 4 fermion operators,
When you integrate out to
which gives
So
you the
there's
Yukawa.
typically again new gauge
Yeah.
group in the
Yeah,
world.
which
there's a
which
heavy,
then-
there's a heavy boson and
Yes.
Yeah. So no one has a good model for this, but
So then you claim that you solve the problem associated with S, but you don't solve the problem of flavor in this new model.
no, not yet. Yeah, so the first thing is really to come up with a good model which, well, it does not gives you this, the dynamical electroweak symmetry gradient is in agreement with present data. And well, okay, so you don't really know to which group the SU4 breaks into in this chiral symmetry gradient, but the usual assumption is that there is somehow the largest subgroup of this SU4 which is natural, and in this case it's the SO4. So what we will write down is an effective field theory which has this SU4 to SO4 chiral symmetry breaking structure, and has this lightest scalars vectors, and then actually one can also include some composite fermions as well. And you can check that when you gauge the technique quarks in the standard way, well, the well, then the electroweak gauge symmetry is embedded in this SU4 in such a way that this chiral symmetry breaking indeed gives you the correct electroweak breaking structure. And well, this is just the complete Lagrange, or at least almost complete. So I mean, I won't give any details, but this matrix M has the scalar degrees of freedom, and this C has these composite vector states, and then well, you write down all the different couplings, so the strong interaction parts are this part which replaces the Higgs sector of the standard model, and then you have the interactions between the scalars and the vectors, and then I've also included all the standard model terms, at least almost here. So I have also written down the Yukawa couplings. Well, I don't want to go into details, but actually what we will, I will not now go to the the final temperature calculation which we did. So in this case we actually didn't consider the vector measurements at all. So what we were using was basically only the scalar part of the theory, which I will explain in more detail in just a few minutes, and then we coupled also to the standard model.
So the Yukawa part is just, you don't care where it comes from, I mean.
No.
Originally.
So you just take the standard model as a right,
yeah.
How you
put scalars and vectors in there, of the scalar in there, yes.
Yeah, you can. Okay, and then I will just mention that we did some, with this, the complete Lagrange, well, actually we were using the next minimum of the technical Lagrange, which is slightly simpler actually than what I showed you. We did some LHC phenomenology, basically the production of these vector states, which should be very well visible in the Drell-Yan LHC. But let me then go to the final temperature calculation, and for that I will explain to you a little bit on the scalar sector of the theory which we were using. So the matrix N which appears here is, well, actually it's so this is a quark bilinear, so its transformation under the SU4 is that's such that it's so this is a 4x4 matrix first of all. So it transforms under SU4 in such a way that you multiply it by group matrix from both sides. So it's here the Q is the array of these four Weil spinors, which have this like this fundamental SU4 transformation. And what you have is you have actually this 2x2 block matrix is the whole 2x2 matrix is made of two Higgs doublets, which are the most important states, where you have this composite Higgs, and then actually you cannot make this complete under this chiral symmetric transformation without introducing these partners, the pseudoscalar partners theta of the composite Higgs, And then you actually have the goldstone bosons, which will be even by the standard model gauge bosons, such that they come to longitudinal components of the Z and W's. And these also have some scalar partners. And then you have these composite scalar baryons, which, well, are actually not so important for this final temperature study. And well, these include also some extra goldstone modes which are related to these SU4 to SO4 chiral symmetry breaking, which are, well, which don't receive a mass from the chiral symmetry breaking, so you have to assume some, well, extended technical mechanism which gives a mass to these guys, because otherwise, well, you don't want to see any light extra states, because, well, you would have seen them already. But, well, actually you can also give a dynamical mass from coupling to the electroweak sector to these guys.
So that these O particles have technic quark and anti-technic quark, and these other baryons have two technic quarks.
Yes.
And because they are in adjoint representation, they are both techni-neutral states,
Yes.
of course, but in principle you can have three technic quark states also, or any number of technic quark states. This is as opposed to fundamental SU2, where you can only have these two quark states, but here, because it's adjoint, you can have three quark states. Have you considered their mass?
Yeah, actually in the plots which I showed you, we assume that this ETC mass scale, which is so high that these states are completely decoupled from the dynamics. Then you have only these states.
Yes. You can also have actually a technic quark and gluon, technic gluon
so
states.
These are
so
the fermion states, where we also did not include in this study. We just did the most simple thing because, well, you expect that you expect that these states are the lightest ones.
Sure, they are associated with the chiral.
Yes.
Sure.
And then, well, particle to the Higgs, then you have these scalar states are expected to be strongly coupled to the Higgs, which then, well, through this chiral symmetry breaking, well, this is just the analog of the standard model Higgs, so this will get the vacuum expectation value, which is related to the chiral compensate in this case. And so, okay. So this is now the most important thing is now how to describe this dynamics of the scalar. And you have some free parameters. This actually this anomalous term, which is, well, this actually this coupling of all these turns out to be rather important for the dynamics. And, well, you have the 4 free parameters in this like Higgs potential, but one of them is fixed by the electroweak scale, and you are left with 3 free parameters which we, well, identify we relate to them with by using the 3-level mass expressions to the masses of the Higgs, the pseudoscalar partner of the Higgs, and then also the scalar partners, the mass of the scalar partners of the goldstone boson. So this is just a redefinition of the parameters. So I will use these parameters for plotting the various things. And then you also have the masses of these extra leptons which you have introduced. And then you also have to have the scale of the EDC interactions, which, well, for the plots, which I will show you in a minute, is actually, but you have to assume that this is a large number.
What was the B in there?
So yeah, so this is a generator which commutes with all the SU4. Well, it's, well, it's a basically, so this, I mean, it's a 4x4 matrix, diagonal one, which has some, well, it's not the unit matrix, but has some, well, it's just diagonal and has some numbers. So it's, I think, well, this is the minimal operator which you can write down in order to give masses to these extra Koshno modes. So I don't know now recall exactly how we come up with this, the exact form of the P, but it should, at least it should commute with the SU2 cross SU, well, SU2 left cross SU2 right. Generally.
So it's a constant matrix,
Yeah,
there it's not any field.
And so, yeah, and then I will tell you how we actually calculated the effective potential. So we take the Lagrangian, which we have the scalars which are coupled to the standard model, and this is kind of the standard calculation. So you calculate the effective potential, you include the tree-level potential, basically multiplied by the Lagrangian, and then also the one loop term in the effective potential. Okay, in this study we only used the three first terms in this effective potential at high temperature. But we checked that it was actually not. Oh, for the standard model, we actually relevant at this scale are only the top quark and the electroweak gauge bosons. The rest of the standard model particles are so light that they don't affect the phase transition at all. And well, we also included the one loop green resummation of the one loop. Well, it is one loop temperature dependent by using the method introduced by Eskimos. So this is just a straightforward calculation by using the Lagrangian, which we have. And then you can calculate the phi c over Tc parameter. I'm sure that you know what this is. You identify the critical temperature, well, where you have, well, the broken vacuum and the symmetric vacuum are exactly degenerate at the end. But for the potential in terms, well, as a function of the Higgs expectation value, and so on. Then this parameter is defined by the ratio of the.
So why is the phase transition strongly first order in this model?
Well, you have lots of bosons, so that's typical.
Yeah.
So you, and then you, well, well, that's the main. Of course, you will also add these heavy fermions, but then you can play with the masses of these extra bosons and the heavy fermions in such a way that their contributions to to the potential practically cancel each other. So that
Can
this is
we
actually
trust the
what happens in
perturbative
this
calculation
relation.
here?
Okay, so this is what
Up to 100.
Plotted in terms
so you can
of
have
the
100% difference.
of the Higgs mass and the mass of the pseudoscalar partner of the Higgs. And well, actually in this region there is no phase transition at all in this walking. I mean in this effective potential calculation. And basically this ratio actually goes to infinity. Well, if you would include more terms in this high temperature series, then you could see that this number goes to infinity here. But anyways, there is a reasonably large part of the parameter space where you see that this parameter is larger than 1, which, well, as you probably know,
Is there
It's
any
the-
particular value of MH that you expect, or?
no, you don't really know. Well, you can, well, not really, but these are being studied on the lattice, so we hope that at some point.
So this is the one loop effective potential
Yes.
before, which treats, once you have the effective potential, this effective degree of freedom is just a degree of freedom. I mean, it's just a Higgs. But
Yes.
you've picked up all sorts of other degrees of freedom in the process. Is that
Yeah.
I mean, sorry, I didn't see in detail, but the potential for this M matrix
Mm.
is like a Higgs.
Yes.
potential.
No, I mean
Like
the
for-
tree level potential is just like in the standard.
Right. So the difference now is that because you went via doing Technicolor, you have extra degrees of freedom, which now gives you different
Yes.
contributions.
Yes. And what I didn't say, this is actually very similar to the 2 weeks doublet model.
Right.
You exactly have basically two Higgs doublets, but then this chiral symmetry structure somehow tells you how these must be coupled.
Right. So there's some constraints and parameters you wouldn't have in the original.
Yeah, I think so.
Yeah, you have lots of parameters, of course, in the effective Lagrangian,
Yeah, but
and I imagine that.
yes, but now by assuming that the ETC mass scale is large, I only have 4 parameters, which are, well, I plot in terms of the Higgs mass and the mass of the theta, and then I have these additional parameters. Well, actually to see this strong phase transition, you need to assume that the Higgs must be quite light, and these scalar states, which are the partners of the goldstone, also should be quite large. If you take them heavier, well, you still have some, well, region, yeah, but you cannot take them very heavy. So this is well, at least you can exclude this kind of scenarios at the LHC.
So CP violation would still be in those terms that you just at the moment have put in down. It's just
Well, at the
usually
moment
cover
we don't
stuff.
have any CP violation.
Right. But in principle, they should be in the same mass
Mm.
terms as you coming from this extended, etc.
Yeah.
In the usual way.
So, F is a new Fermi, what is it? So,
Yeah, so that's the mass of the new fermions.
and there is how come it can be so light? There is no bound on this 150 GeV Fermi?
Well, if I recall, there is no. I think the bounds are of the order of 100, and it's also dependent on how you couple.
So how does it compare to?
Yeah, I mean, I think the count should be of the order of 100 CV. But I'm not too familiar how you count.
It must be weakly coupled on the. So
But anyways, it's also, well, you can take it to be heavier also. I mean there is no strict reason why it should be so light. Well, you can, well, actually I probably have some plots also. Well, at least in the paper we also plot this for 350 CV.
And it doesn't change very much.
No, so the region where it's strong moves. Okay, well.
So these are those masses what you have there. These are the zero temperature masses.
Yes, these are
Oh,
zero.
and at the transition itself, they are all much lighter, presumably.
Yes.
So that makes it strong.
And well, I'm basically out of time. I will just tell you what I've been working on recently. So this is for the production of gravitational wave. Well, many of you probably know what these parameters are. I have no time to explain, but I've been calculating, and well, there is some very tiny region of parameter space where you can produce very strong gravitational waves, but this is really, really narrow. And well, then I have also slides for the ultra minimal technicolor, but maybe I don't want to use it. We had done just the same calculation, but now you have different chiral symmetry. Actually, more complicated thing because you have two different sectors of technicolors. So you have two transitions, two chiral transitions. SU2 to SP4 and SU2 to SU2. So there are some you can just do the same and study how strong the phase transition is. It's actually a bit weaker than this well you
How close are the two conditions?
well, that also, I mean, in temperature, that also depends on the parameters. That's also one thing which we study. So you can come up with some phase diagrams where you have as a function of temperature and then some parameters of the theory. For example, the Higgs mass. You see that, well, the line where you have the like the transition 1 is the blue line, and the transition 2 is the red line, and then you have you expect to have at some point where the critical temperature of the two transitions are equal. And then when you actually couple these two sectors of technique works in different representations, they are coupled through technical gluon exchange. So you expect to see some coupling effects. So you can, there is also this funny possibility that as a function of temperature you may break the electroweak symmetry twice.
What is a typical critical temperature?
Well, it's of the order of 100 GeV. It varies a lot with the
Can it
parameter.
be much higher?
Yeah, well, yeah, but usually then the fire rate T is smaller because it has T in the denominator.
Probably Higgs mass is higher too.
Yeah, the mass is also higher.
Yeah. You lose the first order transition.
Yeah, you typically lose the first order. These are actually what you see in this ultra minimal technicolor. Using the one loop effective potential. with some very specific values of the input parameters. But that was all I wanted to say. So I think the main points were that these walking technical models pass the experimental test, and then you can study them by using the effective field theories, and then we have done this finite temperature analysis for the minimal walking technical, where there's a possibility of having a vertical transition, and also ultra minimal technical, where you have these two transitions, and then this fine possibility of having electroweak symmetry where probing flies, and then we are starting the gravitational wave production.
So when you say that you have different phase transitions, so you have different scalars which can coincide.
Yes, you have. So you can come up with
So the first phase transition could happen at much higher temperature.
Yes. Well, well, they are anyways. So you expect that the scales of the two different sectors are linked through this strong interaction. So you don't expect that they are too much different from each other.
But can you get like 300 GeV?
Yes. Yeah.
You know,
I think-
this is interesting because
Yeah, but-
that's in the range where you can observe them, while 100 GeV is not
Yes,
so...
yes.
so-
But the problem is that then you typically, at least in this model, you lose the first order phase transition when the temperature is high.
So what's the status on whether they are walking or not? I mean,
Yeah, so that's.
okay, I'm supposed to ask that.
Well, here I guess it's not really relevant for your studies with the effective theory
No, sure.
or the 3D. Of course, the origin of that comes from some kind of
Well,
walking scenario.
it's not very motivated that if it's not walking, at least of the
Yeah.
couples.
Sure.
So what is the walking used for then?
I mean, you need that to get rid of the flavor change in neutral currents.
Right.
So if it's not walking, yeah, at least. So I think there is basically no way to get rid of the flavor change in neutral currents if it's not walking.
I mean, this Technicolor itself is a very nice idea, of course. I mean, it's so closely related to QCD, but this extended sector of it looks so messy that is there a way somehow? I mean, how much is it restricted? Could it be something completely different? I mean, if you assume that you have at this ETC scale base something completely different, I don't know, string theory, brains and extra dimensions where it originates, is I mean, that kind of scenario possible? Has anybody ever considered?
Well, I don't know. I think there is quite much freedom.
But, so you said this is testable at LFC.
Yeah, well, this particular model is just.
You have quite light states typically.
Yes. Well, you don't really know what is the mass scale of the lightest scalar, but at least it seems that you, for this first order phase transition, you need to have them very light. So if you don't see them at LHC, then you probably don't have the first order.
Yeah, I mean, but they cannot. I mean, it's like they have to be of order Higgs mass. I mean, that's the natural scale, because Higgs is one of the mesons. The others should be of this on the same ballpark, and Higgs is not even the light meson of the chiral symmetry breaking.
So you said there are some lattice calculation of the Higgs mass? You are
The Higgs is very tough to measure. I mean, the Higgs is the is the problem, and of course you cannot determine the Higgs mass in this theory. I mean, in the sense that Higgs mass would be the input parameter then, I mean, which you use to fix the scale, because you don't have any other way to fix the scale there. I mean, you have to use the Higgs and the
Yeah.
vacuum expectation value of the Higgs to fix the scales of your lattice theory. So to you, it's
So
not bound.
Francesco has some argument on the Higgs mass which relies on QCD. So you somehow take the sigma mass in QCD, which is 660. So then you use some large NC scaling argument to, you first go to large NC in the like some representation and then come back in other, because they agree at large NC, and you see that you expect to have from that argument you expect to have this adjoint, I guess, due to a light composite scale.
But you have to fix the scale somehow of the light theory. I mean, like in the QCD, you know that the sigma is 660. I mean, it's 660 only because you fix the lambda QCD to the value where it is. So that same thing here. So that you have to somehow argue that it's in a particular range. And I'm sure you can make arguments. I mean that you use some kind of, I don't know, edge conditions that this is the most likely values, but a priori, of course, it could be in principle anything. But the Higgs is very tough to measure. What is much easier to measure are the vector mesons, the Goldstone bosons, which are then eaten away by the electroweak phase transition, so that they are not directly observable. But in principle, you have other particles here which are of the same ballpark than the Higgs, like these 3 quark states. And those masses we have measured, and many other people have also estimated. And in principle, they are the same ballpark than the Higgs is, so that if you find Higgs, you should start seeing signals of some extra particles, either mesons or fermions. They can be also fermions.
Can you show again the plots with alpha and beta wires?
I mean, oops, wrong card. Oops. No. These ones are the.
No, not this one.
This?
This one.
Yeah, well, I hope you can see the numbers.
Yeah, so you really need like 5 over t of much larger than 1 to get alpha for the 1.
Yeah, I mean the line of, well, you have here 0.2, and that seems to correspond to something like 3.
Beta average is 700.
So the,
700 for
well, this, yeah, 200, 400. So I mean 0.2 is the same as something like 400.
How are you doing the calculation for the gravitational waves?
Well, we are not, well, what I've been doing is only the calculation of these parameters. So I'm working with Chris Kuvaris at NPI, who is looking more at the gravitational wave production. I know that there are some, well, there is, well, some development in this calculation.
That's why I was asking.
So I mean, there's a paper by Riotto and Sannino and some others where they look at the dark matter particle, and it was some meson of the Technicolor, if I remember correctly, Technimeson. And what was the reason why it doesn't decay? Or
Well, if you choose the, well, there is this, well, you can, okay. So in order to cancel the triangle anomalies, you have to choose the at least one way to cancel these anomalies. Well, anyways, when you cancel the anomalies, you are left with one parameter which affects the charges of these. The new technique works. And then when you make these baryonic scalar states, the charges of these states are affected by this free parameter. So you basically can choose the charge.
Yeah. So it was a technique
So
baryon actually.
So it's these technique baryon states, and then you can choose the charge correctly.
So it would consist of technibaryons and anti-technibaryons. And if they meet, they will annihilate, probably. Or maybe, you just, if the cross-section is so small that they don't annihilate very easily, so then you could have
I'm not too familiar with the dark matter.
I think in these models he was trying to relate the baryon asymmetry to dark matter energy density, so he has to assume that there is an asymmetry.
Maybe even asymmetry, I see.
He wants to explain the ratio between omega baryon and omega dark matter.
The only thing which I can say about the dark matter is well, one of the motivations to considering this more complicated model is that it has a better dark matter candidate, which is actually the baryon. It's a state which is related to this. Well, this second sector, which is actually not charged under the electroweak. So I think you can come up with
In some sense that would be baryonic dark matter. Well, I don't mean with the characteristic of baryons, but it is.
It does not carry baryon number.
No, not at all. It doesn't carry baryon.
Okay.
Right, so I think there's wasn't there some director's coffee? Some of the people next door.
Oh, it's I guess.
But they're
Yeah.